actually record on this computer for once. So let's go ahead and talk about Sudoku. Okay. So, which is the other recursion puzzle. So let's go and open again one of my favorite websites of all time, Wikipedia. Now, not reading, being a reader of Japanese, something I'm like learning on again and off again. I don't know how good Japanese, native Japanese Wikipedia is, but for computer science articles and really niche stuff, like Wikipedia is the best. So, okay, Sudoku, predecessors, number puzzles began appearing in Japan in Paris like this. Modern Sudoku was most likely designed anonymously by Howard Garnes, and it was introduced in Japan by, it was first published as Number Place. I mean, so like you got a game like this, it's not completely unprecedented that it would appear like multiple times throughout history, but it was the Japanese version incarnation of it, so to speak, that caught on. So roughly translated. So one thing that Israel and Japan seem to really like, by the way, is their abbreviations. That seems to be something that the culture shares. For instance, Sudoku has this full name, Suji wa Dokushin ni Kagiru, which means the digits must be single. This is like similar to the Israeli Secret Service being like the Institute for XYZ. I forget what it's called, but everybody just simply shortens it to the Institute, which is Mossad. So, but anyway, we've got, so here, a later date, it gets abbreviated to Sudoku. So, and then it started spreading. Yeah, in 1997, Hong Kong judge Wayne Gold partly completed puzzle in a Japanese bookshop. Over 6 years, he developed a computer program to develop unique puzzles rapidly. Knowing British newspapers have a long history of publishing crosswords and other puzzles, he promoted it to the Times in Britain, launched in 2004, calling it Sudoku, and then it kind of just took off from there. Pretty much see it anywhere. People don't necessarily associate it with Japan, but it's a very much a, started in Japan as a Japanese phenomenon, even though like it's got all these kind of other histories about seeing it in France and the like. It is a really exciting, it's a really interesting game with lots of different variations of it. Now, what's interesting about Sudoku is that it is a NP complete problem in general, which is really, really interesting. I mean, so like here we can see, like search for it, NP complete. Hey, this is from University of Tokyo, I think. Yep. So, yep, University of Tokyo. So complexity and completeness of finding another solution. So basically what they're talking about is that they show that this is a NP complete, that if they generalize it out, instead of being a 9x9 grid and it made it more like a 16x16 or n/n, right? It was an NP complete problem. So what the heck does NP complete mean? Because I just threw a term at you like I assumed you knew it. NP completeness means that it is this special kind of, we have this special formal definition for it that's, I mean, heck, again, we're on Wikipedia. Why not use Wikipedia to show you what that special formal definition is? NP completeness. NP complete, I guess it does have a pretty easy one. A brute force algorithm can solve it, and its correction for each solution can be verified quickly, and the problem can be used to simulate any other problem with a similar solvability. I'll get into that. What we're saying is that we don't know basically, and there's this interesting thing about P versus MP. If you're interested in it, in learning more about this, computational complexity zoo. There's this great YouTube video, which I love, I'll drop it in the chat. It's 10 minutes long. It's very, 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 very awesome. I'm not going to make you watch it now but if you want to know more about the mathematics of computer science in a really easy to explain way, it's really cool. So what does NP complete? It stands for non-deterministic polynomial time. Basically, it's saying that we can solve this problem in polynomial time, where we can solve it in n to the dth time, like n to the 5th time, n to the 6th time, n to the 10th time, so long as we can access as many parallel universes as we want full of computers working on the same problem. One way to put it. Another way to put this is that basically that we can, so NP-complete problems are this class of problems where we can solve the problem in, where we can solve the problem. The problem is solvable, but it takes a long time. And to do so, we pretty much have to check every single combination for it, which takes like forever, like that BOGO sort problem, right? It's like trying to, the classic one is traveling salesperson, where basically we're asking somebody to go, where you're a traveling salesperson and you've got to go to all these cities. In which order is visiting the cities the most efficient, be it by either cheapest or the least amount of time, right? So you can freely choose the order, but the only way to know which is the cheapest route is to look at all possible routes, which is a factorial problem. So now here's the kicker. While these problems are hard to solve, they are easy to verify that your solution is correct. So you can check to see if your solution is correct very quickly. So NP-complete problems, layman definition, hard to solve, easy to check that you have a solution. Think about that for a second, right? I give you a problem, a Sudoku puzzle. It might be hard to solve that one, but checking to see if the answer is correct, that's not so hard, right? All you have to do is just verify the rules. Okay. So what the kicker is number 2, which is that any NP-complete problem can be used to complete any other NP-complete problem. Any NP-complete problem can be transformed into the NP-complete problem you are trying to solve. So that traveling salesperson problem can be transformed into Sudoku and the other way around too. Or into something called 3-SAT, 3 satisfiability problem. So if you solve one of them in a very efficient manner, then you've solved all of them in a very efficient manner. This is an unsolved problem in computer science, the P versus NP problem. Is there an efficient solution? This problem is worth $1 million. It is one of the unsolved problems in mathematics, is one of the major unsolved problems. So and what I mean by unsolved is that we don't know, we don't know if there is a solution or not. We can't definitely say either way. Okay. So regardless, this is a great video. It talks about these kind of problems, and it also talks about problems like chess, where problems like chess can't be solved in the same question. Like, how do you solve what move to do next in chess? I don't know. That's like your opinion, man. I mean, you got to use some heuristic, but to solve the chess moves, you got to be able to calculate like all possible moves and then make one, and then adjust based off what your enemy is going to make, which can completely change your prior calculations. So anyway, I've gone off on a tangent, but I really want to talk about NP completeness. Check out this video if you want to. It's pretty cool. So let's talk about Sudoku and solving it. So Sudoku, again, is going to be following the same kind of pattern we did. And I'm going to help start you off on this, because what I see is a lot of students, they have problems starting the Sudoku problem, right? They know how to create their board, which is like, hey, I'm just going to create a int, PSVM. I'm just going to create a int array board, just like I did last time, except it's going to be a 9x9 board, right? That makes total sense to everybody, right? It's 9x9 squares. Okay. But then they get to the point where they're like, okay, right, so my solve method, public static Boolean solve method right? That's going to take in the board. That's going to take in the board. And now I'm just going to put return false here. And now you're stuck. I'm just kind of stuck because like what I should pass in is a position. But how do I know what position I'm at? And so a lot of students, what they do is that they do what they'll do is a nested for loop to find what position they're at. So for row is equal to and while this works, I don't like it, and I'll explain why. For I column if board row column equals 0. So I'll find an empty square and I'll start from there. And then they do the rest of the code in here, which involves yet another for loop. And so you got this nested mess of loop, and it kind of doesn't feel recursive anymore because you have to search for where you are. And that's not the way the recursive backtracking is really useful. You should always know where you are. So the answer is I should always know where I am, and I just need to pass that in. So I'm going to pass that in. So my position is a row and a column. So I'm just going to pass in two things, a rint row int column. Okay, so now let's go ahead and format our base cases. What are our base cases? My base case for this is that I should have so first off, how am I doing Sudoku? The Sudoku says basically I'm going to go left to right until I go, and then when I'm done with one row, I'm going to go on to the next row, right? So I'm going to go one row at a time, and then when I'm done with one row, I'm going to go on to the next row. Okay, so here's what I'm going to do. If my column is out of bounds, if column is greater than or equal to board.length. So if my column is now out of bounds, I'm going to say column is equal to 0 and row plus plus. What did I just do here? Well, what I said is I'm going to go, actually, it doesn't matter, but the way I'm explaining it is, if my column is out of bounds, I'm going to go down to the next row and start at the beginning of the next row. Make sense? Because finishing a row doesn't mean that you're done. That just means you're done with that row. Now, on the other hand, if we get to this point and if row is now greater than or equal to board.length, now if we're out of rows, then we're done. We reached the end of the puzzle. Return true. The only way we can hit this point is that if we've solved up to this point, right? So that takes care of that base case. There's also one more base case, which is kind of unique to this puzzle. Okay, so this is where the other thing that trips students up, which is, what about all those spaces that are filled, right? Unlike the other puzzle, unlike the unlike the chess puzzle where you're given an empty chessboard, in Sudoku, you're given something that's not empty. You have a lot of spaces to fill. So what do you do? Okay, well, some of these spaces are filled. So that's another base case though, right? Again, this is all about making local decisions. You're trying to make your decision for this square. And if your square is filled, then you just want to go on to the next square because you're done with this square. So if board row column is equal to, if that is not equal to 0, so if it's not an empty square, right? If board row column is not empty, then what am I going to do? I am going to go on to the next square. So I'm going to return solve the next square, please. Board row, and that will be column plus 1. And here, part of why I like doing what I did above us is I don't have to worry anywhere else about wrapping around. And just say, do the next square. That's plus 1 to the column. That's the next square since I'm going from left to right. And then this, the method that I'm calling is going to take care of that. That method that I'm calling is myself, but hey. Okay, so now we are in the solve method. Now we are in basically the same kind of thing we did over here, where the is safe method, right? So now for every possible choice at this square, we try that choice, right? Yep, this is, and actually for once we're going to use I. For I is equal to 1, less than or equal to 9, because the number has to be 1 through 9, right? I can also put board.length if I want to generalize it, right? Because it will be 9. So we're going to go through all the numbers 1 through 9, and we're going to try them all. Now, the less than or equal to is important here, by the way. So we want to try all the possibilities, and we want to ask if can place, I'll say, if I can place on this board, row, column, if I can put I in this row column combination on this board, then awesome, I'll do so. Also, I'm not programming in Google's Go, so I need to surround this with parentheses like that. And I need to actually make this method. And again, so there, return true. We'll return to this method in a moment. Okay. So if I can place it here, I do so. Make sense? And when I'm done with this method, if I get through this method, and you'll want to finish it up just like you did this one, essentially. But if I can't do anything, I'm just going to have a safety feature over here in case we forget later. If we have to backtrack, I'm going to clear this square, just in case. I find this good practice. That if we have to backtrack, we set our current square to 0 so that we don't forget about it later. Okay, so next, and also don't forget about this return operation in line 16. There's a lot of mistakes, a lot of bugs that I see happen, and I'm looking for it in the student's code, and then I realize, you forgot to put a return statement in line 16. And so when you solve it and you backtrack, you'd actually continue on to trying to change the square that you put in, which is a bit of a mistake. All right, so let's talk about the can place method, which is like the is safe over here. Actually exactly like that. I just called it something else. Now, just like this one, where we have is safe, we can, and actually I'll go ahead and change it to, no. Just like we can, just like we did for the chess, we can check these three, we need to do 3 checks on this row column. We got to make sure that there's that I isn't already in this row, I isn't already in this column, and I is not already in this 3 by 3 square. So rather than returning true, what I'm going to do is create 3 method stubs. So return row check, row check, and call check, and square check. And I didn't fill out their parameters because they all have the same parameters, which are the parameters I just passed in here. And by doing it like this again, we can test, you can write each one independently of each other and test each one before moving on to the next one. That way, you know, when you're trying to figure out what the bug is, you can know that, oh, it's not row because that already worked. So we'll pass in I, row, column, board. So we'll pass in, we just got to pass in these parameters, the same parameters everywhere here. And we're good. And so now I'm just relying on, and now this will go ahead and create them all for me. So, or I thought they would. Return true, probably because I didn't create there. Return true, call check, create the method, return true. So now that they're all returning true, I mean, it's going to be the same where basically anything we put in is going to be fine. You'll get a board with a lot of ones, but now you can modify it. And I'll just put them in the order which I suggest you do them. And so now you can work on them one at a time, which is pretty awesome. So basically you just got to fill this out, which is just a matter of adapting what you see over here into the context of Sudoku, which is not that hard at all. And then fill out these methods for Sudoku. I'm going to go ahead and drop this in the chat for you all, so you don't have to worry about copying it down with a possible mistake. So you're going to get it. Oh, right. I forget. I don't need to drop it in chat like this. I'm just going to go ahead and go whoop in there. So I sent you the Java file. That way that I don't have to break it up into multiple messages, right? And that way you don't have to worry about furiously copying it down. Okay. Yep. So just fill. So hopefully this has elucidated matters, made things a bit more clear with regards to how this one is supposed to work. Any questions? All right. So I got your exams back to you. If there are issues with your exams, please let me know. Or if you need some explanations as to why you lost points on something, please let me know. It's also possible I made mistakes. Fortunately, in this case, it's not possible I made an addition error because the computer takes care of adding up the total score. But it is possible that like I entered in the grade wrong for a question or two, or I misinterpreted your code or something. So just let me know. Okay. So stop share and stop.